our new context. So the school jazz band is playing at Sweet Yo's, a frozen yogurt shop. And some information about that is that it costs $5 to get in the door for the event. Now, if you'd like to eat froyo while you are listening to their tunes, you can fill up your cup with yogurt and toppings for 40 cents per ounce. So I think it's like one of those yogurt shops where you just fill your bowl, do it yourself. They have one of those scales that you just set it on and weigh it before you pay, and this is the price. You don't have to buy frozen yogurt to use the school jazz band, but it's an option. So we're going to take a look to, we're actually going to work through all of the questions here on this first page. So similar to how we did this earlier in the week, I'm going to give you some more time to read carefully what each question is asking, try every problem, and we'll come back together in a little bit and we'll go from there. All right, so let's take a look here at number 1. So here we wanted to write an equation that will give us the total cost in dollars. So today we're having Z represent the amount of dollars. For attending the event, think it's ordering Z ounces of the frozen yogurt. So what we need to think about here, the total cost is going to be that $5 to get in the door. We only have to pay that once. You could add the 5 at the beginning or you could add it at the end. And then it's 40 cents times the number of ounces. So if we had something that was 7 ounces, we would multiply the 7 ounces by 40 cents to get that cost of the yogurt, and then add on the $5. So 0.40 times Z. Z is the number of ounces. All right, so all we're doing in number 2 is we're using that equation we got in number 1. We're evaluating this for a specific value of Z's. We're just plugging in 14 for the Z, and we see that that total cost would be 10.60. Now in number 3, we are working backwards. So now we know the amount of money that a student brought. So they brought $10 for the event. We want to know how many ounces of frozen yogurt they can buy. And so here we're plugging 10 in place of a dollar amount. Let me think about something there. So here we're just thinking about working backwards. And so the steps that we did to get to our final answer, I wrote those out in red. So first thing we're doing here is we're subtracting 5 from both sides. We need to subtract out the cost to get in the door. And then we need to figure out how many ounces it was. So when we divide both sides by 0.40, 5 divided by 0.40 ends up giving us 12.5 ounces. So she doesn't have to get exactly that amount. It might actually be hard to fill the cup and like perfectly equal that. But technically that is how much she could buy with the amount of money that she has. All right, so let's think about this in terms of a function. So there's another real-world example where we have an input and an output, and we have some equations here that are being written. So going back up to the very first one, we can think of this, what we wrote in number 1, as being a function. I'm going to use an F here, where the input is the number of ounces, and the output is the number of dollars. So going back to the original equation, and we saw that's what we did in number 2, is we knew the number of ounces, we plugged ounces in for the variable, and what it gave us was dollars. I'm also going to circle and label these in our story problem. So again, ounces are the input, and dollars represented the output. Now, another thing that we can do here with our function notation to match this with the variables D and Z that we were using in the problem is we could just use a Z to represent the number of ounces, and then we could use a D to represent the number of dollars. So we can say F of Z equals D. In fact, what we did in number 2 is we did F of 14, we plugged in the ounces, and it told us that it was 10.60. The output was an amount of dollars. All right, let's take a look now at the next part. So we're going to go into number 4, and it's kind of a similar question to what we just did in number 3, but now we have a different dollar amount. Hold on, where's my number 4? We'll go back to this. Hold on a second. Okay, I don't know how that question got forgotten about. But that's going to be the same idea here. So we're just going to plug in $7. On the left-hand side, we're still going to think about subtracting 5 from both sides. Then we'll divide by both sides by 0.40. This one actually works out nicely to end up being 5 ounces. So similar process, slightly different answer because she had a different amount of money. All right, so the steps that we actually just did for number 3 and number 4, thinking about starting with a dollar amount, working backwards to figure out the number of ounces, that is what's going to help us with number 5. So let's go back to this screen. So now we want to go the other way, and we want an equation that's going to give us the number of ounces based on knowing how much money you bringing D dollars. So it's kind of like when the student brought $10, the first thing we did with that is we subtracted out the $5 fee to get in the door, so we would just do D minus 5. Then any remaining money, that is reserved for the frozen yogurt bowl. So to figure out the ounces, we'll just take that amount of money on the numerator, divide by the price per ounce, which is 0.40, and the answer we get is going to be the number of ounces. So I want you to write down a few extra things here for this equation that we did in number 5. And that is that we have now switched the input and the output. For this function, now the input is dollars. If you know the amount of dollars, we can input that, plug that in where the D is. And then the output was the number of ounces. And we have a special name for this equation. This version, where we're going the other direction, is called the inverse. Now, if we were to put this into function notation, there's a special way that we indicate that something is an inverse. First of all, to connect this with the input and the output switching, let's just notice here that for this function, now we are inputting a dollar amount, and the output is number of ounces. The symbol, though, for an inverse actually looks like this. I'm just going to write it off to the side here. I'm going to put a box around this. So in this version now, we can still see that when we input a dollar amount Z, it's going to output ounces Z. And what looks different, though, is we have this little -1 up there. It almost kind of looks like an exponent. It's not, but it is a little -1 there. This means the inverse of the original f function. So that's what that symbol means. All right, so let's try to write here. Oh, here we go. Sorry. The top of that sentence, some of the words got cut off. Okay, so let's look at what it's saying here in number 6. So it says Henry bought 10 ounces of froyo, and we want to think about what equation we should use to determine how much money he spent. So we actually have 2 versions now of an equation that is relating D and Z. Well, this would actually be a good one to go back to the first equation from today. And that is because we know the number of ounces. We're inputting ounces, so we can just plug 10 in for Z. And we're trying to work to figure out the cost in dollars. And we see it ends up being $9. All right, now interestingly enough, let's look at the connection here with the next problem. In number 7, it says Chandler spent $9 for the evening. Let's look at what equation we should use to determine how much is froyo weighed, in other words, how many ounces did he get? Well, now, if we know a dollar amount and we're trying to work backwards and figure out ounces, this is when it would be beneficial to use the inverse version of the equation, because we're going to be plugging in a dollar amount. Here we have the steps to do to the dollars, and it's an output, the type of thing that we're looking for. So notice that we plugged in that $9 for D, we're working backwards, and not too surprising, we end up with 10 ounces, which was connected to what we did up here in Henry's problem. So remember, Henry bought 10 ounces, he spent $9. Well, if Chandler brought $9, he could buy 10 ounces. So we're going forward, and then we're going backwards, and we're getting right back to the same number that we started with. So one extra little piece that I'd like you to put off to the side here in number 6 is 10 ounces. For number 6, I want to give you a little visual here. So we started with 10 ounces. We're going to plug that into the original function that we call f. So f of 10, that was the first equation that we wrote, and the output was $9. Then, for Chandler's problem, it's kind of like we took the $9, so now we're thinking about that as our starting point. And we did not plug that into the original equation from today. We plugged it into the inverse. We decided, well, the inverse made more sense to plug into. So we plugged it into F inverse. When we did F inverse of $9, the output got us back to where we started with 10 ounces. All right, the other interesting thing that we can see here, thinking back to inputs and outputs again, if we look at Henry's process, we had an input of 10 ounces, and that gave us an output of $9. Well, in Chandler's equation, we had an input of $9, and that gave us an output of 10 ounces. So here's what's really happening with this. A couple things are happening. So when we're looking at the inverse, the input and the output switch. The meaning of what they are switch, dollars and ounces switch places. The actual numbers here, we see that they're switching. But the other thing that's interesting is this is kind of like what we did with the function composition back on Tuesday, where we started with a number, we plugged it into the first function, we got an answer, then we took that answer and we plugged it into the second function. And so there's actually another way that we could write this connection between Henry's problem and Chandler's problem, and that looks like this. So it would be doing F inverse of f of x. So it's kind of like we started with, now I'm not going to do an x there, I'm going to do, let me put the, what was our amount that we plugged in? That was the 10 ounces. Okay, let's connect it first to our numbers. So it's kind of like we just did f inverse of f of 10, okay? So hang with me. So if we start with the f of 10 in the middle, that's what we did here, right? F of 10 is 9. We got an answer of 9. Then, when we did f inverse of $9, well, when we put $9 in the inverse, it got us back to where we started. Our final answer was 10. So f inverse of f of 10 equals 10. Notice how the 10s are exactly the same. And this will actually always be true no matter what the functions are. And so one interesting piece from today, the way that the inverse is related to the original function, f inverse of f of x is always just going to equal x, whatever number you have there in that position. All right, so going back to our two learning targets that we had at the very start today, the first one was just about being able to write an inverse function. So on this first side here, let's say writing inverse functions. And here's the big idea. So we're going to put this into a sentence. We can use inverse operations to rewrite an equation so that the input and output variables switch. Okay, so when we did this here in our activity, we started with the first equation, d equals 5 plus 0.40z. And by inverse operations here, we mean like, so instead of adding 5, what the inverse of that would be is subtract 5. So we're thinking about undoing things. And so for the inverse, we have d equals d minus 5. The inverse operation for multiplying by 0.40 is to divide by 0.40. So we're seeing how we used those inverse operations, but also we're seeing that the input and the output variables switched places. The d and the z literally switched places, which is a characteristic of getting an inverse. All right, and then our second learning target for today, so this is connecting back to what we did on Tuesday. So here we're looking at composition of inverse functions. So what we're going to say on this side here is going to be true for a function f. We'll think of that as being the original function, and its inverse, which is the f that has a little -1. So what we just saw on the other side in the activity is that f inverse of f of x always equals x. Whatever original starting point you plug into your original function, get an answer. Well, if you take that answer and plug it into the inverse, you're undoing all the steps, so you get back to the beginning. It's always going to equal the same number. There is another way that this can go. So if we were to go the other direction, you could actually switch places of the f and the f inverse. So you could actually put something into your inverse function first. So first do f inverse of x, get an answer, plug it into the original f function, and it'll work the same way. You get back to the same thing that you started with. Okay, so we're going to put in another little example here, connecting this back to our frozen yogurt problem. So our original function f, we were inputting ounces, and that gave us an output of dollars. Then for the inverse, f inverse, we put in the dollars, and the output that it gave us was the ounces. And then to think of another visual here of the steps that we're actually taking when we do the composition, it's like starting with 10 ounces, putting it into our F function, that outputted $9. Then we took the $9 and that became the input of the inverse. We did F inverse of $9, and the ending output was 10 ounces. So I'm just going to make a little note here showing, hey, that was really cool. The final answer we got is exactly the same. All right, everyone. So we're going to come back together here and start to take a look at number one. So Penny received $150 for her birthday. Now, she also works at a job that pays $13 an hour. She's putting all of that money into her bank account. So we're going to start by writing out a few versions of an equation that are relating the variables S, the amount of money she saves, and H, the number of hours that she's worked. So in part A, to get the amount of money that she's saved, we want it to equal S. And it says after working H hours, so based on the number of hours worked, well, if she's making $13 an hour, we have 13H, and then we also can show that we're adding on that birthday gift of $150. Now, $150 only gets added one time, like we're not multiplying that by the number of hours. Now, in part B, here we want to think about going the other direction. So we want to figure out how many hours she has worked in order to save S dollars. So let's think about if she had like a specific goal of an amount of money that she wanted to save. Like let's say that she wanted to save $1,000. Think about putting 1,000 in place of the S here. Well, then what we're figuring out to get from here to here is, okay, like what would I do to this number to work backwards and solve for H? Well, the first inverse operation I'm going to do, I'm going to think about subtracting 150 from both sides. Well, that's what I'm doing here. S is whatever her goal is, what she wants to save. We're first going to subtract 150. And then, whatever that remaining amount is, we would undo this. We undo multiplication with division. So we would divide that whole thing by 13. So this is what it would look like putting it into like a formula. And then the output is going to give us the number of hours worked. So kind of like in the other problem we did, both equations have value depending on what you have and what you're trying to find out. So if you know how many hours she's worked, use this one. Figure out how much she can save. If you know how much she wants to save, use this one. That's going to tell you how many hours she has to work. Now, let's think about what's happening here in part C. It says that we want to verify that these functions are inverses using composition. So composition is what we talked about over here in the second half. This little kind of flow chart down here at the bottom, if this statement ends up being true, then yes, our functions would be inverses. And I wanted to give you two ways that you can think about doing this. One option is to use an actual number. So just pick a number to represent number of hours worked. And it doesn't matter what number you choose. I'm going to maybe just try this with 10 hours. And I'm just going to see what happens if I plug 10 into my first equation. I can see how much money she will have saved. So it looks like that would be 150 plus 130. So it looks like she will have saved $280. Okay, so I get an answer. Now, if the second equation I wrote truly is the inverse, that means that when I plug in that answer, I'm going to plug in the $280, and I'm going to see if I get the same answer that I started with, which was 10 hours. So let's try this. If we do 280 minus 150, that equals 130. And then sure enough here, if I do 130 minus 13, I get back to 10 hours. I'm going to put a little check mark here. That was using composition with a specific value. Now I said there's two ways you can do this. So I want to actually, I'm going to put a little line here. On this side, I'm going to show you another way that you can do it just using the variables, so not actually needing to plug a number in. Well, if we're thinking about composition, we could make these function names a little bit more clear. So yes, it's S, but it's really S of H, because H is the input on the first one. This one down here is really H of S. So the output is hours, but the input on this one is how much we saved. And so using composition, using the equations, there's two directions that we can go. Let's look at the first one. That would be plugging the H function into the S function. So look at what happens here. This entire H function, S minus 150 divided by 13, that's going to get plugged in for H right here. So across the top here, instead of writing 150 plus 13H, I'm going to write 150 plus 13 with a big parenthesis, and I'm going to plug in the whole function for H, the S minus 150 over 13. And then here's what's really cool. When we try to start to simplify this down, let's look at the 13 multiplied out in front here. That's going to actually cancel out with the dividing by 13 on the fraction part. So those are going to go away. Then we have 150 plus S minus 150. Well, the positive 150 in the front is going to cancel out with a minus 150 behind it. And what we have left is we're just left with S. We're equal to the same thing that we started with. Right here. That's what we're wanting. So that would be a way to show it. I'm going to put another little check mark there with the equation. Like, yeah, I plugged one equation into the other. Like, everything canceled, and we were just left with S. There's one more direction, though, that we could go. We could have done H of S of H. I'm going to switch colors here and do that one in green. So that's where we're going to take the entire S function, 150 plus 13H, and actually plug it in for S right down here. We're going to put it in the H function. So the numerator part on the H function is now going to be 150 plus 13H minus 150. The whole thing is still divided by 13. Well, lots of things are going to cancel again. Look, the 150 in front is going to cancel out the 150 at the end. Then we have 13H divided by 13. The 13's cancel, and it's just equal to H. Another little check mark. We proved that, yes, going both directions. We looked at the equations. They are inverses. We tried it with a number. That also showed that they were inverses. Now, a slight variation of this, like let's say instead of you coming up with the equations and then testing it, let's say that I gave you two equations, like the two equations on the back of the room that we had at the start of today, like f of x and g of x, maybe they're equal to something else. And I said, hey, are these inverses? Well, you can check this, and if it doesn't end up working in this way, then no, they're not inverses of one another. There's different ways that we can utilize that tool. So we're given some information about how many minutes it has been sitting out and the degrees Fahrenheit. And we're seeing that this makes sense. The longer it sits out, the more it's going to cool down. That temperature is going to decrease. All right, so here we're thinking back to evaluating a function using a table. So h of 13, well, the function here represented in the table is h of t. So the 13 here is representing a time period, number of minutes. So that's the entry that we're looking for in the table. H of 13 equals 77. Here's what we want to make sure we include, though. We want the interpretation for what this means. We're going to connect it back to minutes and degrees. So it just means that 13 minutes after the hot chocolate was prepared, it was 77 degrees. All right, now look at part B. Look at the notation here. This is asking us for an inverse. So inverse is where the input and the output switch. So now 107, that's the input of the inverse, that doesn't represent minutes, it's going to represent the other variable, which was the temperature. So we are going to find when the temperature was 107, and we see that that happens as when it was sitting out for 5 minutes. So the interpretation is a similar sentence, but this is the inverse. We're going the other direction. We're starting with the temperature. So here we say, well, when the temperature was 107 degrees, that means the chocolate was sitting out for 5 minutes. That's a way to think about working backwards. So when you're looking at these tables, it's kind of like when you have the original function, the input, that is going to be whatever you have in your column or row that represents your input, like the X column compared to the Y column. When you have the inverse here, it's kind of like you're looking at what was the output of the original function. The output of the original function now becomes the input of the inverse. Always thinking about going the other direction. Okay, so we're finding h of h inverse of 77. So it's a composition, because there's two ofs, a function of another function. Let's think about starting on the inside. So h inverse of 77. Well, 77 is going to represent a temperature. Working backwards, we can see that that is equal to 13, because it was 13 minutes when it was 77 degrees. Okay, so we just evaluated the little inside part. That was equal to 13. Okay, but we're not done. Now we need to do the outside part. Now we're going to find h of 13. Well, now the input of the original function is a time in minutes. So now we're looking back to when it was 13 minutes. We want to know the temperature. Well, isn't that getting us exactly back to where we started with? So the answer there is 77. Because we're doing a composition of a function and its inverse, notice that it follows that rule. It's just exactly the same number as what we had on the very inside at the very beginning. We have different representations for functions. We can do it with an equation, with a table, or a graph. We've looked at the other two. The graph is the one that we have not done yet, thinking about inverses. And so notice here that this graph that they've given us originally, this is f of x, so the regular f is always the original. And look at the questions that it's asking us. It's asking us questions all about the inverse. And so it's kind of like just going the opposite direction. So if we want to find f inverse of 3, that means f of something is equal to 3, so that if we did the inverse, f inverse of 3, it's going to equal that original input that we started with. And so what's really happening is it's kind of like if we think about labeling on our graph here, the x-axis, those are like the original inputs for f. The y-axis represents like the original outputs for f. So it's kind of like we're trying to figure out from the graph what input would have resulted in an output of 3.
4.
Is it 4?
I think so.
Let's see.
Or is it the other way around? Is it 1?
One other tip I will give you for the assignment, if we take a quick look here at number 4, the advice I wanted to give, so there's one problem that's kind of like this one, where, so we're starting with an equation, h of x equals -2 times the quantity x plus 9. What we want to do is we want to find an equation for the inverse. And one thing I was going to tell you is you could simplify this. Instead of thinking of the left-hand part here as the full-on h of x, you could shorten that like what we did in the activity today and just think of that as being h. Sometimes I think it's easier to think about, like working backwards and undoing these things when you just have two separate variables, so like we just have h and then we just have x. It's also, I think, a little harder sometimes to think about it out of context, but if we're trying to figure out the inverse, that just means that we want to work backwards and ultimately get an answer that's in terms of x, so we want to get x equals. So it's kind of actually like something that we did back in chapter 1, where we're just rearranging things, doing those inverse operations, like, for example, dividing both sides by -2. We would have this at the beginning, and then subtracting 9 from both sides. And that would be, that's our answer. So that's our inverse equation. We got the other variable by itself. Now, technically, connecting it back here to the problem, they want to define p of x to be the name that you give to the inverse. So we could actually just like make it a little bit more formal, again, right at the end, like make it a p of x, but it's the same idea.